Hi everyone, I'm going to give my talk about quantifying cardiac-induced brain tissue deformations using dense MRI. So I will first start with some background information, which was already provided by Jack on the first day. But the brain is pulsating, which can be nicely seen in this amplified video. It's largely amplified, but it still nicely shows the pulsations of the brain. And these pulsations drive fluid flow through the brain. And this provides blood supply away from the brain. And if we could measure these brain tissue motions, that would give us some insights in the mechanical tissue properties of the brain, go into the underlying vasculature in the tissue. So a method to measure brain tissue pulsations is by displacement encoding with stimulated echoes, also shortened as DENS. And that's an acquisition technique with an encoding and decoding gradient with a mixing time in between. And since this mixing time is relatively long, very small displacements can occur, and therefore during the acquisition you use a cardiac triggering. In this case, we use the ECG triggering based on the ECG signal. We look at the R-top of the ECG, and then after the R-top acquisition takes place over the cardiac cycle in order to cover the whole or at least a part of. Based on the acquisition, we can compute a volumetric strain, where volumetric and in our data we look at the R-top as a reference. So therefore, the volumetric strain we're looking at is the systolic phase of the cardiac cycle. And this volumetric strain can be nicely approximated by the summation over the brain. This has also previously been done by IODD Adams, where he measured volumetric strain using the 7T scanner over the whole cardiac cycle. You can nicely see that at the beginning, at 0, the brain is the smallest, and then there's an increase in volumetric strain, and then the brain goes back to the original state again. So it follows the cardiac cycle very nicely. Here you can see an example of these volumetric strain maps. At different moments, at different cardiac phases. And you can nicely see that a lot of the brain is expanding. So all the red parts are positive volumetric strains, but there are also some parts which are more compressing. For example, here at the sagittal sinus, there seems to be some compression going on. And also a bit deeper in the brain, there are also some compressed voxels. So we were intrigued by this, and we were wondering, is it possible that parts of the brain compress during the systole? Because you expect the whole blood pulse to come in, so everything to become larger. However, due to the Monroe-Kelly doctrine, we know that the whole brain is encapsulated by the skull, and therefore, if the blood volume of into the brain is mode of this app, it can be squeezed into. And this has also been measured. Measurement of strain and we measured CSF outflow in the spinal canal. You really see that there's a difference between the two curves, which led to the black curve. But since the volume in the brain has to stay constant, this difference also has to be compensated somewhere else in the brain. And assumingly this can be done by the larger vessels, where, for example, venous blood is squeezed. Similar phenomenon is seen in the coronary arteries, where the myocard and here even the flow through the coronary system. So all these thoughts and these measurements led to the idea that there might be some systolic compressions in the brain tissue. So that's what I dove into. And the method I used was twofold. So first I did a clustering method. And in this talk, I will explain both of these methods to you. So the first method is based on a count map. I used 9 healthy subjects. And again, the volumetric strain is always relative to the reference state, so the R-top. All these volumetric frame maps are labeled each voxel either +1 or -1, which can be seen here. So a positive volumetric strain is labeled +1, and a negative volumetric. Since I have 8 cardiac, I did a summation over all the cardiac phases of the label. That led to a count map with voxels ranging from -8 negative cardiac phases, +8 when it was positive phases. And the resulting image looks like this. Going on in the brain, but more often compressed than expanded. So to quantify this a bit more, size of the positive ROI and the negative ROI, where the positive ROI is the expanding ROI with all the voxels being larger than 0, and the negative ROI is the compressive area with all the voxels being smaller than 0. And I took the mean of each ROI to see how it looked like. Well, the results for this map were that the expansion ROI covered 65% of the whole brain map. We also saw that the curves followed the cardiac cycle. So here on the left figure, you see the volumetric strain map for the whole brain. And this curve is quite similar to the curve Adams created, which I showed at the beginning of the presentation. So it's as expected. And then the expansion ROI shows a similar pattern, but with a bit higher strains in it. And then interestingly, we see that the compression ROI also showed a similar pattern, but opposite to the expansion ROI. We also did something. We saw in most subjects that there was a compression going on at the ventral sinus, the white arrow. And we also saw that there seemed to be some compressions going on in a bit deeper brain areas, where these brain areas are less contaminated by, for example, larger veins or other structures. So it's more logical that there is some pure tissue compression going on there. So all these results at least triggered our interest, and therefore we decided to do a different method, which is a bit more established. I used the same subjects again, but and I determined the optimal number of clusters using the sum of square distances for several number of clusters, which gives a range of clusters that is, it was best represented. And the optimal number of clusters for this case was 4. And then after clustering, I did it for all subjects, and it led to 4 clusters, of which I took the mean volumetric strain within each cluster. We ranked the clusters from cluster 1 to cluster high to low, and we also looked at the division of the clusters over the brain maps. Then if you repeat it for all subjects and lay over the clusters in one plot, you can nicely see that, especially for cluster 1, 2, and 4, the clusters show similar behavior. And you should note here that variance, because the y-axis have different. In cluster 3, there's differences range more around 0 instead of showing this mild compression error. So therefore, for averaging the size of the clusters, we looked at the 5 subjects that showed similar behavior. Yeah, we saw that the expansion cluster, so cluster 1 and cluster 2, covered 94.3% of the brain map. And the compression cluster, cluster 3 and 4, covered 5.7% of the brain map. And note here that's a big difference from the ROI we find in the count map. Right side, this is multiple slices for one of the subjects. You see the division of the clusters over the whole brain. And what you can see here is that the largest part of the brain shows expansion, so cluster 1 and cluster 2. But then cluster 3 and 4, the compressive clusters, are mostly located in locations around the ventricles, so in the middle of the brain and a bit under interstitial sinus. Some hotspots around sulcis are also showing compression. And this can maybe be better seen in a figure where it's overlaid on the T1 image. You can see most compressive voxels are located at the ventricle. There's something going on at the sagittal sinus. There seems to be something going on the right side of the sulci. But also on the left figure, you see that there are two compressive dots in the basal ganglia, which could be caused by, for example, the perivascular spaces, which were mentioned earlier. However, to look at the question we asked, is there tissue during the systolic phase? I want to mention that there's a difference between the compressive ROI in the count map and in the clustering map, because we saw that the voxels that the largest part of the behavior in this cardiac compressive curve is in the count map. And if you would leave out all the voxels that came out of the clustering but didn't, or came out of the count map but didn't, if you leave all the compressive voxels out of the count map, if these came out of the clustering, you would see that the behavior didn't show this cardiac compressive cycle anymore. And also, if you look at the spatial distribution, it shows that it's more likely that the compressions we see is caused by larger veins or sulci or structures that allow some fluid flow away from the brain. Some different but however, the spatial classifications can be very useful, especially knowing where these extreme veins. So to conclude, we did some observations on compressions in the brain. These compressions probably reflect some changes in fluid-filled spaces, such as sulci, larger veins, rather than the compressions of brain tissue itself. But it definitely provides some useful knowledge about events data, which you can use for further analysis.